Hi everyone. In this video we're going to look at a few different types of examples that we could see using definite integrals, whether that's using properties of definite integrals or using some of the rules that we saw, or using the definition of a definite integral. So to get started, we're going to take a look at just kind of a graph that I'm going to go ahead and hand draw in here. That's always a little dangerous to have a hand-drawn graph, but I'm going to try to label things very clearly here. So let's say we have a graph that does something like this. And these are lines. This is a linear piecewise function, so you should be able to kind of piece together, no pun intended, what the function values here look like. Okay, so go ahead and see if you can kind of come up with, and maybe I shouldn't even use function when I'm drawing straight vertical lines like this, but the question is, can you come up with, just by looking at this, the integral from 0 to 4 of f of x dx? So this whole thing is f. This is a piecewise function. Can you come up with the integral from 0 to 4 of f of x dx? Okay. And this piece right here, maybe don't view it as part of the actual function there. Maybe it's more like this as a piecewise function has a jump discontinuity right here at x equals 3. But if you remember from the last video, a jump discontinuity is not a problem. Just think about kind of going to one side of that jump discontinuity and finding the area under the curve, and then starting at the next spot or the beginning of the next interval of that jump discontinuity. So the integral from 0 to 4, give you a second to kind of work through that. Here's how I would split it up. I would try to split it up like this and look at kind of section number 1, section number 2, and section number 3. Now keep in mind that when you have a section that is below the x-axis, that area is technically considered to be negative because we're thinking about the area between the x-axis and the graph. So if you look at the area of, we'll call it region 1. Let's see, that has a base of 2. It has a height of 2. That looks like a right triangle the way that I've drawn it. You may remember the area of a right triangle looks like 1/2 times base times height. So it's 1/2 times 2 times 2. The area of region number 1 there is 2. And then for the area of region 2, you can say, well, that has a base of 1, it has a height of 2. That is 1/2, because it's still a right triangle, 1/2 times base times height, so 1/2 times 1 times 2. So the area of kind of region number 2, that right triangle that's in there, would be, let's see, 2 times 1/2, you get 1 in there. And so it looks like if you were to add together triangles 1 and 2, you would get 2 plus 1 is 3. Now be careful, because triangle number 3 over here, this area number 3 again is below the x-axis. That's going to be negative. So as a whole right now we should have 2 plus 1, but then we're going to have minus something. Now 3 has a width of 1, a height of 1, so the area of region 3 is just 1/2, but we're going to subtract 1/2. So 2 plus 1 minus 1/2, there we should get 2.5, so 5 over 2 as our area of the whole thing. So we have some positive, some negative. Now, not every example is going to use kind of a situation like this where you have linear functions as your piecewise function, or as the pieces of your function, I should say. But some of them do look like this, and others you can kind of approximate where you might have, if you kind of split up your grid into little cells, I would say like 1 cell units like this, and kind of count how many cells you have, is another way you can kind of think about doing that. It's easier on graph paper, on an actual grid that's there, but you can kind of visualize where you have most of a cell and include that, and then if you have just a little small part of a cell, then maybe don't include that when you're adding things up. But just some ways you can kind of approximate or estimate what that might look like. Okay. Some other examples we could take a look at involve some of the properties that we saw in the last video. So I'm going to give you something like this to start out with. Let's say we have something like the integral from 1 to 4 of f of x we don't know what f of x necessarily is. Remember, we always need a dx, so the integral from 1 to 4 of f of x dx is equal to 5. The integral from 1 to 4 of g of x, a completely different function, is equal to negative 2. Okay. We could also look at the integral from 4 to 7 of f of x dx is equal to 3, and the integral from 4 to 7 of g of x dx is equal to 7. Now, we don't necessarily know what f of x and g of x are, but that doesn't mean we can't find anything out about what happens when we use some of these rules. For example, one of the things we could find is what is the integral from 1 to 7 of f of x dx. Okay, go ahead and take a second, see if you can figure out what that would look like. And you can think about using one of the rules that we had in the last video. If you want to pause this and go take a look at the rules that came up in the last video, that might not be a bad idea to see kind of what rules should you use. I'll give you a hint. Another way to split up this integral is to write it as the integral from 1 to 4 of f of x dx plus the integral from 4 to 7 of f of x dx. And so it does matter that where the first integral ends, that's where the second integral starts. And if you're kind of graphing something like this, granted we don't know what f of x and g of x are, but if you're graphing this, the first part here says what's the area from 1 to 4 under the curve of f of x. The second part says what's the area from 4 to 7 under the curve of f of x dx. So you can add those two areas together to get the total area that you started with. Now, the integral from 1 to 4 of f of x dx, we know what that is. We know that that's 5. That's given to us up here. So you can kind of use that and plug that in. And then we're adding the area of the integral from 4 to 7 f of x dx, okay, which we know is 3. So it's kind of just looking over here and saying, well, which one do I have? Which one do I need? Okay. Now, some of the rules that we also had from the other day actually give us another interesting case. Sometimes there's something sneaky that shows up in the homework or in a book or somewhere. They just try to trick you a little bit, and this is an interesting thought. It's also kind of neat to visually think about this. Something like, what is the integral from 4 to 4 of f of x dx? Now, this is a little bit weird, because remember what we're talking about here is the area under a curve from one value, so from A to B. But the problem is, if A and B are both the same, then, okay, that's a little weird. It's saying kind of like start at 4, like it doesn't actually matter what your curve is here. Start at 4. So there's kind of your leftmost part of your interval, and then just end at 4, like don't move, basically. So you can think about, well, what's the area under f of x there from 4 to 4? Well, that's just going to be 0 every time. In fact, no matter what your f of x function is, if you start and end in the same place, you're going to get something. You're going to get 0 there. All right, so this video is all about a few different types of examples that we could see show up. And I wanted to look at one other type of example of estimating the area under a curve using rectangles, using Riemann sums. Because you'll remember that a little while ago we looked at how to find R4, or doesn't have to be 4 rectangles, but that's what we looked at, was R4 and L4. And there's actually other options as well. Our book doesn't hit every possible option that you could have in there, but there's another one that I want to take a look at. And so let's use a function. Here's f of x equals x squared, and let's go from x equals 0 to x equals 2. But instead of using R4 or L4, now what I want to use is I'm going to use something called the midpoint. And so I'm going to use what we're going to call M4. 4 means there's still 4 rectangles. I'll tell you what, we've done a lot with 4 rectangles. Let's mix it up a little bit. Let's go from 0 to 3, and let's go with 6 rectangles. Get a little bit more creative. So 6 rectangles. Now we're still actually going to find the width of those rectangles in exactly the same way. We're still going to find delta x, just like we did a couple of videos ago, by doing b minus a divided by n. So it's still going to look like 3 minus 0 divided by 6. We're still going to have a width of 1/2 there. And you know what f of x equals x squared looks like. It's going to be something like this. We're basically going from 0 to 3 and trying to estimate the area under this curve. Okay. So let me go ahead and get a new screen so that I can draw this a little bit bigger. We have something like this that goes from 0 to 3. And instead of using a left-hand sum or a right-hand sum, we're going to use a midpoint sum. And so what this does is it basically says you still want to split up your area from 0 to 3 into increments of 1/2. So it's going to be there's a 1 in there, there's a 2 in there, there's a 0.5, there's a 1.5, there's a 2, there's a 2.5. Okay. Now the difference here is that when you look at let's see, it would be 1/2 as your delta x. We would throw that out front and have parentheses. Now, quick question, how many things are going to be added up inside of the parentheses? Does it make sense that there should be 6 things added up? So 6 terms inside. That's because we have 6 rectangles now, not 4. Okay, and so, but we want to be careful about what is the output values that you're using. F of what? Right, earlier, if we were doing a left-hand sum, we would start with f of 0, and then use f of 0.5, and f of 1, and f of 1.5, and we would have used f of 0, but not f of 3. In a right-hand sum, we would have used f of 3, but not f of 0. But a midpoint works a little bit differently. It says that instead of having the rectangle touch your graph on the top left corner or the top right corner, use the middle. Use the middle of the rectangle. Now this is hard to draw on something like this, but it basically says make your rectangles so that they cross the graph in the middle of the rectangle, not on one of the ends. Okay. Now you might say, oh, that's kind of hard to do, and it is. But here's the thing: if you know where the midpoint is, so what's the midpoint between 0 and 0.5, you know you need 0.25 as your first midpoint. What's the midpoint between 0.5 and 1? You need 0.75 as your second midpoint. What's the midpoint between 1 and 1.5? That's 1.25. Kind of the same thing for all of these, and you should find 6 different values that are midpoints of the left and the right hand edge of those rectangles. So 1.25. What about between 1.5 and 2? You need 1.75. Between 2 and 2.5, you need 2.25. And then between 2.5 and 3, you need 2.75. So these are your x values that you're going to use in your function in order to find M6. The formula is almost exactly the same. You're just using different x values. Remember, these x values come from averaging together the left-hand side of the rectangle and the right-hand side of the rectangle. So to find M6, it's going to look like 1/2 times, let's see, our function here was x squared, wasn't it? So let me see where to start as 0.25. Okay, so 0.25 squared plus 0.75 squared plus 1.25 squared plus 1.75 squared. Don't know why I'm putting parentheses every time. That's not needed. Plus 2.25 squared plus 2.75 squared. Did I get 6 of them? 1, 2, 3, 4, 5, 6. Yep. And so I should have 6 things that I'm adding together inside because it's M6. And each of the x values that I'm using in the function comes from the midpoints. And then I'm still multiplying by delta x out front because that's still the width of each of those rectangles. Okay. So you can do this and figure out what you get when you add all those together. But that's the idea of doing M6 instead of R4 or R4 or L4 or R6 or L6. You can use a midpoint there as well. Okay. So just a few different types of examples that you might see show up in this section, all having to do with integrating. And remember, what you should be thinking about is anytime you hear the word integrating or integration, that means the area under a curve from A to B. Hope you've enjoyed the video. Good luck practicing.